Okay guys, previously discuss natin yung one-dimensional wave equation last session. Okay? At ito yung ating na-derive formula. The square of the velocity of the wave times the partial derivative is equal to the partial derivative where time is fixed or constant in relation to location or x. So this is the general form of what we call the one-dimensional wave equation. We will continue that by discussing the what we call the compressional waves on a spring, no? So para ma-imagine nyo, ito yung kanyang actual demonstration ng compressional waves sa isang spring. So, nakikita nyo dun sa demonstration kung ano yung compressional waves. So, meron din tayo ditong picture. So, nakikita nyo ito dito. Ito yung na-compress na spring ng wave. Okay, kaya ang sabi dyan, ang tawag ay compressional wave o na slinky spring. Yan. So, itong wave na to, nakikita natin nagta-travel kasi as it travels, kinocompress niya yung spring. No, pinagdidikit-dikit niya. Okay. So, yun natin didiscusin, no? Paano i-compute yung speed, no? Yung velocity ng compressional wave na to. So, we begin by defining the Hooke's law. Okay, sabi sa Hooke's law, T, which stands for tension, is equal to K times L minus L0, no? Where L0 is the unstretched length of the spring. Ito yung unstretched hanggang L0 tayo. Ito. Dito, no? Yung full length, kapag dinagdagan natin ng tension, ito yung T. So, T is equal to the difference, no? K times the difference of L, which is the full length, and the L0. Now, suppose that we stretch the string an additional amount of which we call the change in L. So, itong equation na to, dadagdagan natin ng change in tension plus, yan, lalagyan natin ng tension kasi magdadagdag tayo ng additional na length. Ibig sabihin, baba natin din yung spring. So, this will be its formula. Simplifying, we will have K times the change in L minus L0 plus K times the change in L. So, with this, using equation 76, we are left with the change in T or tension is equal to K times the change in L is equal to KL times the change in L over L. Okay? There are two reasons why we have written change in T as KL times the change in L over L. The first is that change in L over L is the amount of stretch per unit length. A quantity engineers call strain, no? Ito yung tinatawag nating strobe. Kapareho din siya ni strain, no? In this case. So, makikita nyo yung spring, may certain location siya sa ating figure. So, the same way with the strobe, no? So, remember yung strobe is the series of images. So, ito yung sinasabing stretch per unit length. Yan. Yung position niya is the length of each specific spring. So, another reason is that the engineers would call this inherent property KL of the spring as a spring modulus. So, we have two properties. One is the stretch per unit length, which we call the strain, and KL for the spring modulus. To describe the stretch spring, we will introduce the function yx that represents the displacement of a point on the spring from its equilibrium. Pag sinabing equilibrium, yun yung kanyang initial position, no? Ito yon, equilibrium. Kasi ito yung hindi pa siya nababanat. Wala pa siyang tension dyan, no? So, from here, nilagyan natin siya ng tension. So, nagkaroon siya ng change in L, which is change in length. At pag sinukat natin to from here, from the left to the right, okay, we will have the full length which is represented by L. And makikita natin dito yung tension. At yung difference, LO and the full length L is the change in L, which is represented by our Y of X, which is the displacement. So if we differentiate YX with respect to X, we get, ito na yung ating derivative. We will have the change in L over L. Thus, for a uniformly stretched spring, the local strain or stretch of Yx is equal to dyx over dx is the amount of stretch per unit length. So, ito yung ating strain. Okay? So, the strain is represented by dyx over dx. Okay? So, to have see that the yx is equal to dyx over dx is a local amount of stretching per unit length, we will have the following derivation, no? Where YL is equal to the change in L, the total displacement at the end. So, ito yung makikita nyo sa video as it moves back and forth. That is the displacement. So, from 0 to the change in displacement or Yx, it will produce what we call the net force on the change in X. So, going back to equation 77, we will have the change in tension is equal to KL times the change in length over L. So, babalikan natin yung video. Balikan natin. Okay? So, makikita nyo to. This is the change, no? Yung kamay na yon which is going back and forth, no? Inihila niya yung spring back and forth, that is the change in T, which is the tension. And it will produce or is equal to the KL times the change in length over L. At makikita natin dito, this gives us the formula for the tension Tx at point X. So, at a certain point nung spring, ito yung sinasabing tension Tx. So, meaning, kung ititigil natin yung ating video, so at a certain point, this point, yun yung sinasabing tension X. Okay? Kapag tinigil mo siya, ano yung tension na narito? Ito yung sinasabing point in X. So, it is equal to TO plus KL Y X. Where TO is the equilibrium tension, yung hindi pa siya nahihigit, and KLX is the change in tension caused by the displacement of the parts of the spring from their equilibrium position. Ito yung nagre-represent dun sa isang movement lang. Okay? Specific na formula for the tension Tx. Pero itong pag sinabi mong change in Tx, ito yung continually changing, no? So let us now apply the equation 82A to a short section of the spring of the length. Remember, ito yung hindi gumagalaw, di ba? Specific position, specific tension ng spring, no? So i-apply daw natin change in length or change in X. Okay? Applying that, lalagyan na natin ng movement. So, as X goes to X plus change in X. So, ibig sabihin, nag-change ng location yung dulo ng spring or yung hand gumalaw, then it will produce a net force on the change in X, which is equal to the tension times X plus the change in X minus the original position of the tension X. Okay? We will have the following net force on the change in X is equal to KLAX, change in X times, ito na yung wave, no? Ito na yung change in the tension. Okay? Change in location. Kung natatandaan nyo ba, this is the formula for our second derivative. Ayan, kita nyo, ayan. The second derivative of Yx with respect to X. The net force is the second derivative. So, this is the same way as saying na this is the acceleration. no? The change in velocity is equal, or the acceleration of the object is the change in velocity of the object. Yun yung ating unang discussion, no, about derivatives, di ba? So applying this dito sa ating spring, the net force is the change, or is equal to the change in the tension and length of the spring, no? If the spring has a mass per unit length, now we will apply the mass, no? Kakaroon ng wave kasi nagmo-move yung mass ng spring kasi nagsasama-sama siya, di ba? So if the spring has a mass per unit length, okay? So kailangan nating i-apply to as shown in this equation. The change in mass is equal to the per unit of the change in x. So yung mass na yan, yun yung result, no, as the spring is compressed. So, yan yung nakita natin, nako-compress yung individual spring niya, no, as the wave moves from right to left, no, dun sa ating video. So, if we allow the waves on the spring, the displacement yx from equilibrium depends not only on the position x down the spring, but also on the time. So, we will apply now the acceleration y xt is equal to the partial derivative of y x to xt over dt squared, no? So if you remember, ito yung ating formula for symbol for partial derivative. So t squared ang nasa ilalim niyan kasi fix yung position natin, no? Kung ito ay t naman, kung ito ay x squared naman, katulad nito, then the t is constant. Okay? So, ito yung sa ating acceleration. Now, for the net force on the location, no, change in location of the spring, we will have KL times the change in x times the partial derivative. Okay? So, combining these two by applying the Newton's second law, so we have net force on the change in mass is equal to the change in mass times the acceleration times the xt. So we will have the net force on the change in mass is equal to, or represented as, KL times the change in x times the derivative, where the time is constant, is equal to the mass, ito yung mass niya, times the derivative, which is represented by the acceleration dito sa ating original formula, no? So, manonotice nyo, ito yung Newton's law, which is force. Ito yung force. And the m is the mass. Dito yung mass. And times the acceleration. Okay? So, canceling these two, change in x, we will have the KL over the unit length measure times the derivative is equal to the derivative where x is constant, no? Dito time is constant, dito x is constant. So recognizing 88 as the wave equation, we will have the square of the velocity of the wave times the partial derivatives where time is constant is equal to the derivative where the x is constant. So from here, we can identify the wave speed as velocity or compressional slinky wave is equal to the square root of KL over mass.
We go now with the speed of sound. The analysis of compressional sound waves in air can be carried out along lines very similar to our analysis of a compressional wave on a spring. However, to do this, we need to build on our discussion of the behavior of an ideal gas. Consider a column of gas with a cross-sectional area A and length L as shown in figure 15. Ito yun, ay yung module. So, meron siyang length at ito yung point where we will measure the second derivatives. At ito yung area nung ating cylinder gas. Ito yung piston na mag-exert ng pressure, represented by the change in L. Kasi pag pinush natin to, mababawasan yung kanyang length, therefore magkakaroon ng change in L. And also at the same time, mag-compress dun sa gas na nasa loob ng cylinder na to, no? So we can think of a gas as being in a cylinder with frictionless walls. So let the variable x measure the distance down the column. Yan, ito yon, variable x. Starting at the left end. And imagine that we have a frictionless piston at the right end. Okay? If we pull the piston out a small distance, change in length, we change the volume of the gas by an amount. Change in volume is equal to the area, ito yung area, times the change in length. And so doing, we will decrease the pressure P. So kapag hinila daw natin itong piston a little bit further, ito yung formula representing that motion. No? How much the pressure changes depends upon the way the gas is expanded. If we expand it very slowly so that heat has time to flow into the gas and then temperature remains constant, this is called an isothermal expansion. Then we have the following ideal gas law. PV, meaning pressure times volume, equals nRT equals constant. So where N is the number of moles or molecules of gas in the cylinder, nR is the gas constant, and T is the Kelvin in temperature. However, in a sound wave, expansions and compressions happen so rapidly that there is not enough time for heat to flow in or out, and the temperature changes. Okay? So, dito kasi hindi natin makita yung actual effect, no? So, may papanoorin tayong video from YouTube para makita natin yung actual effect ng sound wave sa gas.
This is a very interesting example of how to demonstrate standing waves in a very visual way. If we get a piece of iron pipe, what we've done is we've cut 100 little holes all the way along the top. Connect one end to a gas cylinder and a sealed cap. What happens is the gas fills the tube and the flames burn equally high all the way along the tube. At this end, we've connected a little diaphragm. The little diaphragm is just a balloon held on by an O-ring, and connected to it I have a speaker. And that speaker now I'm going to use.
Yung balloon na yun yung magbabibrate, which is the equivalent dun sa ating drawing, sa ating figure ng piston, no? So yun yung magpupush ng pressure dito sa gas na nasa loob ng tube. At yung vibration na yun naman yung i-cause nung speaker, no? Which is yung sound ay ipoproduce nitong machine na to, no?
To drive different frequencies along this tube. So let's switch on our function generator. And what you can see, I hope, is a difference in the distribution of the gas along the tube. At a frequency,
so nakita niyo mo yung wave shape, yung shape ng wave.
a fixed frequency of, in this case, 350 Hertz, I'm sending a wave down the tube that gets.
So pag binago niya yung frequency, nagbabago rin yung shape ng standing wave, no, na pinoproduce ng sound dun sa gas. Okay? So basically, yung may gas dito sa loob, so nakakulong siya, so mayroong pressure which is produced by this yung ating speaker dito, tsaka yung diaphragm which is the balloon, no, acting as diaphragm. So habang nagbabibrate siya rito, nagpo-produce ng wave, ng pulse, at dumadaan siya rito. Pagpunta niya rito, yung wave pagdating dito sa dulo, bumabalik siya. Okay? So yung nakikita nyong node, ibig sabihin ng node itong part na walang peak, no, yung pinakamababa, no, tawag doon ay node, antinode, no. So dito sila nagka-cancel out kasi bumabalik yung wave. Okay? So pag labas ng sounds dito, yung frequency niya depende sa frequency, ay magkikreate siya ng wave, pulse wave. Pagdating niya sa dulo, babalik siya. Pero since yun ay pulse wave, yung pagbalik niya dito, may mga kasunod pa siyang mga wave, no? Dito. So masasalubong niya yon, yung mga bumabalik na wave from the left side, masasalubong niya yung coming from the left, from the right, no? Pag nagsalubong sila at a certain distance, nagkakaroon sila ng cancelling out. So ito yung node na yon, ito yung result, no? Dito sila nag-cancel out. Tapos itong pinakamataas na peak ng wave na to, ito yung pinaka-maximum, no? Ito yung sabi natin, maximum displacement. So ibig sabihin, dito pinakamalakas yung kanyang pulse, no? Yung kanyang wave. Okay? So tuloy natin.
Reflected and comes back. And at various positions, it sums together as an antinode, and at various positions, they cancel each other out at a node. These demonstrate maximum displacement of the wave, minimum displacement of the wave, maximum displacement of the wave. If I wanted to measure the wavelength of this wave, I could measure the distance between a node to an antinode to a node right down to another node. That's one full wavelength of the wave at 350 Hertz. Using these two values, I can now calculate the velocity of sound, not in air, but in the butane gas that occupies the cylinder. Let's look at the variation of frequency. If I now increase the frequency, the velocity is constant. What we should expect to happen is that the wavelength decreases as the velocity increases, as the frequency increases. Now what we see is the wavelengths are shorter. I have 1, 2, 3, 4, 5, 6, 7 peaks in there. Last time I had 6. And now at 450 Hertz, the wavelength is the distance from here to here, or you can take it from antinode to antinode.
So yun yung example natin, no, ng how sound waves, no, travels through gas or through air. No, sa example natin through gas, no. Paano ma-measure yung speed niya is the same dun sa ginawa natin sa spring, no. Sa spring kasi nakikita natin yung dito yung galaw nung compress wave, no. Okay? Pero dun sa example natin sa video, hindi natin makita kasi natatakpan siya ng tube, but nakikita natin siya dun sa shape nung apoy, no, nung fire na pinoproduce nung gas. Okay? So it's basically the same dito sa ating figure, no. Iba lang yung kanyang system, no. Dito kasi piston, no. So dun sa video natin is balloon siya, which is acting as a diaphragm. Siya yung sumasalo ng hangin na nagba-vibrate, no, galing dun sa speaker. Okay? So the same principle, no. When we expand a gas with no heat flow, katulad nung pinanood natin sa video, ang tawag doon ay Adiabatic Expansion. Okay? At ang ating formula, no, for this equation is pressure times volume to the Y power. This is a gamma symbol, no, as for the Greek, is equal to constant. So yung Y stands for the constant pressure over the constant velocity. Okay? So it is the ratio of the specific heat Cp at constant pressure to the specific heat Cv at constant volume. Okay? The quantity Y is equal to Cp over Cv depends, as we saw at the beginning of chapter 18, on the number of effective degrees of freedom of the gas molecules. Okay, so depende kung anong type of gas, pero hindi yan yung ating focus ngayon, no? Dito sa ating topic. Ang focus natin is din sa change in pressure, no? So for an adiabatic expansion, to calculate the change in pressure, we change the volume of the gas in the cylinder by an amount of change in velocity. So kung wala pa siyang pressure, no? Before we compress, we have PVY is equal to P0 B0Y, no? Where P and BO are original pressure and volume. So katulad dito, hindi pa siya kinocompress. So 0 pa ang kanyang pressure and yung volume niya wala pa ring change, no? after the expansion, meaning hinila natin yung piston, no? V goes to V0 plus the change in velocity, change in volume. And P goes to P0 plus the change in pressure. So ito yung ating formula. With that, we get PV0 B0 Y is equal to P0 plus B plus the change in pressure times velocity plus the change in velocity Y. So ni-replace lang natin ito with this change, no? Kasi meron na tayo expansion ng gas. We can use the fact that the change in volume is very small. So using that, we can have the approximation 1 plus AY is estimated to be equal to 1 plus YA for a very small value of A. Using equation 96 and 95B, with the PO plus change in pressure equals pressure times the 1 plus the change in pressure over PO gives us the following, no? So after derivation, cancelling out, okay, applying the laws on the solving equation, we will have 1 is equal to 1 plus the pressure P over PO plus the Y, meaning the constant heat, times the change in velocity over velocity 0. After cancelling the 1s and multiplying through by PO, we get for the pressure change on pressure is equal to negative Y PO times the change in volume over V0. If the cylinder in figure 15 has a cross-sectional area A, length L, and we move the piston out a distance of change in L, we have B0 equals AL, that is the area times the length, and we have also the change in volume is equal to A times the change in length. Thus, from equation 99, we have Yx is equal to x over L times the change in L. In moving the piston out, the average displacement of a molecule Yx at position X. No? Ito yon, which is the same as our equation 78. So, like what we did in the spring, we will apply now our second derivative, and we will have the APX is equal to negative YPO times YX, which is represent the local pressure change. We can write this equation in the form PX is equal to PO plus change in pressure X. Also, PX is equal to PO minus Y, PO times the Y times X. So, ito kasi yun, no? Yung change in P or pressure X is equal dito sa ating local pressure change, no? So, i-replace lang natin and we will have this equation 105. Now, consider section of the cylinder of length X or change in X. Ito yon. Consider na natin ngayon to. I-apply natin yung ating derived formula. So, we will have Fx is equal to area Px. Okay? So, i-replace natin to kasi nagkaroon na tayo ng change. F times X plus change in X is equal to AP times X plus change in X. So, yung net force, pwede natin i-compute as Fx minus Fx plus the change in X. This one is also equal to, according to our equation 107, is equal to APX minus PX plus the change in X. Ito yon, no? So, using equation 105, we will have the following derivation, no? So, we will have the net force as equivalent to the area times the constant heat, which is the gamma or the Y, times PO times the change in X times our second derivative application, no? So, as in the case of the spring, we'll end up taking the limit as a change in X goes to 0. Ito yon, we are applying the formula in this specific region or section, no? So, this is the pressure process acting on a small section of gas in our hypothetical cylinder. So 1 point lang ang ating kino-consider, no? That is this the change in x. Applying again the Newton's second law. Again, first we have the net force of YPO times the area times the change in x times our derivative where x or where time is constant in relation to x or the location. And we have also the mass as we apply the Newton's second law, which is the change in mass is equal to the P or the pressure, no? Times the area times the change in x. And also having our acceleration of the gas as equal to the partial derivative where x is constant in relation to time. We will have the following derivation katulad dun sa ating spring. The velocity of the sound wave is equal to the square root of y, which is the constant heat, times the pressure PO over the P. Okay? Ano yung P? Yan. Is the density of the gas, no? So we have another formula, the same with formula 115, no? The velocity of sound is equal to the B over the density of the gas. This B is defined to be equal to the change in pressure over the change in volume over volume. And it is called the bulk modulus, no? And we can see that it is the same, no, with our derived formula in 115. So using the ideal gas law, we can re-express the quantity PO over the density of the gas. We have the E over the density is equal to RT over M. And using that, we will have the velocity of the sound as equal to the square root of Y times RT over M. Kung i-express naman natin in terms of mass of the gas molecules, we will have the following formula. Velocity of the sound is equal to the square root of Y times KT over the mass of the molecule. In our discussion of the ideal gas law, we use the fact that the temperature must a measure of the average thermal kinetic energy of the gas. So, if we want to represent this formula as a measure of the thermal kinetic energy of the gas, so we will have the following derived formula. Velocity of the sound is equal to the velocity times the constant heat over 3. So that's it for our second part of the calculus-based basics 2.